Okay. Hello, everyone. Welcome to the webinar series on Rate Splitting Multiple Access 2021, organized by IEEE ComSoc WTC Special Interest Group of RSMA. This is our fourth webinar, and it's our great honor today to have Professor Xiao from University of Surrey as our distinguished guest speaker. Before the talk, please allow me to make a brief introduction of Professor Xiao. Professor Xiao is now a full professor of wireless communications at the Institute of Communication Systems, home of 5G and 6G Innovation Center at the University of Surrey. He is a technical manager of 5G and 6G Innovation Center, leading the research team in the new physical layer work area and supervising research activities across all the work areas. Before Professor Xiao joined the University of Surrey, he worked at Newcastle University and the Queen's University Belfast. He also held positions at Nokia Networks in Finland. He has published extensively in the fields of communication theory, radio frequency and antenna design, signal processing for wireless communications, and is an inventor on over 10 recent 5G Innovation Center patents addressing bottlenecks problems in 5G systems. Before the talk, I would like to remind the rules of our webinar. During the 15-minute talk, please keep yourself muted and you can type your question in the chat box. After the talk, we will have a 10-minute Q&A session. You can unmute yourself to raise question, or I will choose 2 to 5 questions from the chat. Okay, enjoy the talk. Let me stop sharing my screen. Okay, Professor Xiao, you can share your screen now.
Okay. Thanks, Linda, for the introduction. Hello, everyone. It's a pleasure to deliver this webinar talk. The topic of my presentation is rate splitting applications and error performance analysis. The work was conducted jointly with my colleagues, Dr. Hongzi, Dr. Demi. Credits go to them who did the real work. So we started working on this topic about 3 years ago, after discussion with Bruno. We had some doubts in mind. Basically, we have two questions. First, what are the practical applications of rate splitting? So we like to do impactful, industrially relevant work. The work has no impact if we cannot find any practical applications. The second question is rate splitting practical? Can it be implemented in real systems? We dedicated our efforts in the search for the answers to those questions. So I cannot say we have found all the answers, but at least the work we have done so far can provide some insights and shed some light on those issues. My talk is focused on the broadcast and multicast applications for rate splitting, and is divided into 3 parts. First, we look at a very interesting application of rate splitting in the context of object-based broadcasting, OBB. Then we evaluate the performance, the error performance of rate splitting-based multi-group multicast communications. For simplicity, we focus on single carrier systems first. Then we extend our work to multi-carrier systems. So during the presentation, I will also introduce the joint precoder design and sub-carrier allocation optimization for RS-based multi-group multicast communications. So we know that we have 3 different transmission modes. The first one is unicast transmission, which is the most commonly used mode. For unicast transmission, the message is delivered to one user only. One transmitter, one receiver. For the broadcast transmission, the same message is broadcast to all users in the coverage area. In multicast transmissions, the message is transmitted to a group of users who have subscriptions to this specific service. In some scenarios, for example, in hotspots, the football stadium, in the concert hall, for example, when a lot of users request the same content, it's no point establishing thousands of unicast connections. Otherwise, the network will crash. So in those cases, unicast is not an option. We have to use broadcast and multicast to transmit the same content to all the users. And we are particularly interested in multi-group multicast communications. In this example, we have 3 multicast groups indicated by the red, yellow, and green colors. And we have 3 independent data streams to serve these 3 multicast groups. And each group has 2 users. And alternatively, we can use 6 independent streams to serve these 6 users. But obviously, multicast is more spectral efficient. But we cannot say the spectral efficiency is doubled, because with unicast transmission, the link adaptation can be performed for each user. But in multicast, the link adaptation is performed for the user with the worst channel condition. That is the downside of multicast broadcast transmissions. So why rate splitting for broadcast multicast applications? So what is synergy between these 2? To answer this question, I would like to use some results from Bruno's magazine paper. In the left figures, we see that as the quality of CSIT degrades, whereas the value of alpha decreases, the gap between the rate splitting and the benchmark schemes becomes wider. That means the rate splitting, the advantage of rate splitting is more prominent in the presence of channel estimation errors. In the right figure, we can see that the conventional zero-force beamforming does not work in the overloaded conditions because of the degree of freedom problem. But the rate splitting effectively tackles this bottleneck problem and enables system to operate in overloaded conditions. So those are the main 2 main advantages of rate splitting. Now let's look at the problems with broadcast multicast. The first problem is the CSIT requirements can hardly be fulfilled because some devices are receive-only devices. They cannot possibly transmit pilots. So we have to rely on statistical channel information. And the second problem is the multicast communications usually operate in overloaded conditions in order to maximize the utilization of radio resources. So by reaping the benefits of rate splitting, those two problems can be effectively tackled. So that is where synergy comes from. And that is our motivation to use rate splitting for broadcast multicast communications. The multicast broadcast services were initially introduced in LTE Release 9 standard, and it is called Evolved Multimedia Broadcast Multicast Services, EMBMS. The mechanism is very similar to COMP. We have cluster of cells to jointly serve one multicast group. And the number of participating cells, as well as which cell to participate in the cooperation, are determined by multicast control entity, MCE. And MCE also decides the modulation coding scheme for each multigroup multicast transmission. In this example, we see two multicast groups, but they cannot be served at the same time, because in the LTE standard, the multigroup multicast operates in time division multiplexing mode, and different multicast groups are served at different time slots, causing underutilization of radio resources. And we would like to fully utilize radio resources by simultaneous delivery of different multicast messages at the same time. And that is possible with the spatial division multiplexing enabled by pre-coding beamforming. But the problem with traditional pre-coding beamforming is that it requires a sufficient number of transmit antennas to offer a sufficient number of spatial degrees freedom in order to neutralize the intergroup interference. And we use rate splitting to tackle this bottleneck problem. The single frequency network introduced earlier is most advantageous, is most beneficial for cell add users. Just like COMP, all the cells transmit the same message to a specific group. We literally turn the interference into useful signals. But it has some drawbacks. For example, it requires extended cyclic prefix in order to accommodate a large delay spread from different cells. And it also requires strict synchronization among the participating cells and the high capacity backhaul, because data and the channel information need to be shared among the participating cells. And to tackle those problems, in release 14, we have single cell point multipoint, SPTM, to allow multicast and broadcast within a single cell. This effectively tackles the problems associated with single frequency network. For example, we can use normal CP and the same frame structure as the Unicast. We don't need to have a high capacity backhaul. But inevitably, there will be cell edge problems. So it's a kind of a trade-off. But the MBMS solutions have been evolving. Now we have the possibility to dynamically change the MBSFM area, and we have the flexibility to dynamically switching between SFM and single cell PTM. So we have done extensive work in the area of broadcast multicast in the 5G XCast project. It is a Horizon 2020 project aiming to develop a convergent broadcast, multicast, and unicast solutions for 5G and beyond. And University of Surrey is a leading partner in the consortium, and we have played an instrumental role in the project. And we have identified new broadcast, multicast use cases, such as virtual or VR, AR broadcasting, remote live production, multimedia public warning alert system, V2X broadcast services, massive IoT software and firmware updates, and object-based broadcasting, OBB. Together with our partner BBC, we have developed the OBB testbed. In this demo, a weather broadcast program is delivered as a number of objects, which are reassembled at the user's ends, taking into account their environment and user preferences. Using our testbed, we have theoretically experimentally proved that the multicast transmissions significantly reduce the network load. As we can see, with the multicast transmissions, the network load remains very stable, regardless of the number of devices or users. But on the contrary, the load using Unicast increases linearly as the number of devices increases. The gap becomes wider when we have more devices. And upon the request from the Birmingham Combined Authority, we designed this unidirectional high gain millimeter wave antenna for the upcoming Commonwealth Game to be held in Birmingham next year. It is a fan beam antenna. The beam width is very wide in the azimuth direction and very narrow in the elevation direction, and is down tilted to cover a large area in the stadium. And the radius of each antenna coverage is about 70 meters. So we can use 3 or 4 such kind of antenna to cover the whole stadium. And it's specially designed for Aston Villa Stadium in Birmingham. So it has 8 elements. From the current distribution, we can see the ports, the elements are well isolated. The mutual coupling is minimized. From the ACE parameter, we can see the large impedance bandwidth from 24 gigahertz all the way to 30 gigahertz. And the gain is about 13 dBi. It's a very high gain for such unidirectional antenna. Now let's come back to OBB. What is OBB? OBB is Object-Based Broadcasting promoted by BBC to improve users' quality of experience. Because different users have different preferences and different requirements. For example, some users just want to see the map with temperature and the weather condition indicated on the map, nothing else. Some viewers would like to see the presenter, as the people with hearing impairment would like to see the sign language. Some people would like to see the text. So how can we cater for users' needs with such different requirements? That is not possible with traditional broadcasting. Everyone receives the same content, regardless of the requirements, regardless of user device. Even if they have small device, the screen is truncated like this, the quality of experience is compromised. So this is not what we want. This is what we want. Every user gets what they want. That is enabled by OBB. We break the content into separate objects, which are reassembled at the user's end based on their needs, tailored for their circumstances, preferences, and device. The OBB is a combination of broadcast and multicast. We have the message split into two parts. The first part is common message, which are broadcast to all users. And the second part is private message, which are extra content for specific users in the group. But in rate splitting, we know that we have such kind of common message and private message as well. So therefore, rate splitting is a natural and perfect fit for OBB. Because of the striking resemblance between OBB and rate splitting, therefore, the RS-based OBB can be implemented in a straightforward manner. So we split the message into common and private part. Then we go through the encoding modulation process to derive the transmitted symbols. Then we perform linear precoding on the common part and private part, respectively. But in the conventional linear precoding, we do not have common part, and we do not have the precoder for the common part, and the power constraint is slightly different as well. That's the difference between RS and the non-RS system. To formulate the optimization problem, first we derive the rate for the broadcast message. Then we derive the rate for the multicast message. The optimization problem can be formulated accordingly based on the rate derivation. But there's a difference between OBB and the conventional rate splitting, conventional R system. In conventional R system, we need to optimize both the precoding matrix as well as the splitting ratio C. But in OBB system, the splitting ratio is fixed, predetermined based on users' requirements. But here we only optimize the precoding matrix. To demonstrate the advantage of rate splitting, now let's look at the degree of freedom analysis. First, for traditional precoding. The spatial degree of freedom is the number of interference-free channels. It's defined as the sum capacity at certain SNR divided by log of SNR when this SNR approaches infinity. For a MIMO channel with M inputs and N outputs, the degree of freedom is either M or N, whichever is smaller. The traditional precoding matrix is designed in the null space of other users' channels. To ensure the existence of null space, the number of transmit antenna has to be greater than 1 plus K minus K over M. K is the number of users. M is the number of multicast groups. If this condition is fulfilled, the degree of freedom is 1, otherwise 0. In overloaded condition, the degree of freedom will be 0, and we will have the interference problem, and consequently, we will have rate saturation. But rate splitting effectively tackles this degree of freedom bottleneck problem, because the broadcast message has useful portion of data for all the users and groups, and can be successfully decoded by all the users and contribute to the achievable rate for all the users. So if we split the power into 2 portions, p to the power beta and p minus p to the power beta among the broadcast and the multicast messages, then the degree of freedom for RBB, RS-based OBB is either 1 minus beta over n or beta, whichever is smaller. An obvious choice of beta is to make these 2 terms equal to each other. That gives the beta value of 1 over 1 plus n, and is always greater than 0. So this explains why rate splitting tackles the interference problem and avoids the performance saturation from the degree of freedom perspective. Now let's look at the performance comparison. We compare the proposed RS-OBB system with EMBMS TDM and the traditional linear precoding. The system is overloaded. The condition for the existence of null space is not fulfilled. That's why we see this rate saturation with traditional precoding. A TDM does not have this problem due to the time deviation mechanism, but at the lowest NR, TDM actually has worse performance than the traditional linear precoding, because it does not exploit the spatial diversity gain. But the proposed RS-OBB system has the best rate performance, and that the performance gap becomes even larger when the system becomes more overloaded. In this case, we have 3 users in each group. Here we have 2 users in each group. And in the last figure, we compare the rate performance between 2 private messages, two multipass groups. And they have more or less the same rate performance. That means the fairness is achieved. So rate splitting not only provides a better MFF sum rate, it also guarantees fairness among different multicast groups. Next, let's look at the error performance evaluation. First, we focus on single carrier system. The existing works on rate splitting focus on the sum rate or minimum rate maximization. It's very theoretical, but does rate splitting really work in practice? To answer this question, we need to carry out error performance analysis using link level simulator. Yeah, this diagram is not different from what we saw earlier in the traditional rate splitting system, except we have the coding added between the message splitter and the modulator, and the resource element mapper added after the rate splitting precoder. First, we formulate the optimization problem in order to derive the optimum precoder and equalizer. And to this end, we express the received power of the case user in G-case group in this form. And it can be split in 3 different terms. The first one, SCK, is the received power of the common message. The second part, SK, is the received power of the private message for case user. The third part is the interference, the power of interference plus noise. And the SINR for the common message, common part, is derived as the SCK divided by TK. And the SINR for the private message can be derived as SK over IK. And the rate can be formulated accordingly. Now we can formulate the max-min fairness problem like this. We maximize the rate for each group, and the rate is calculated as the rate of the private part plus the common part plus the private part. And there are 3 constraints. The first one ensures the decodability of the common message. The second constraint guarantees the non-negative rate for the common message. The third one is the total power constraint. And there are 2 parameters to be optimized. The first one is precoding matrix P. The second one is the vector for common rate portions, which determines the splitting ratio between private message and common message. So this optimization problems involves 2 rate components. It cannot be expressed as single SINR. Therefore, this problem cannot be resolved by traditional SDR method. But we can utilize the rate and WMMSC to convert this problem into a WMMSC problem. So once the precoders are optimized, we can derive the equalizer accordingly like this. Okay, first let's compare the rate performance. And we use the non-RS with traditional linear precoding as benchmark for comparison. For the non-RS, the precoders are optimized by SDR and WMMSC method. So this is overloaded system. That's why we see the rate saturation for the non-RS system. But the RS system does not have this problem. Let's choose a target rate as 4/3, which is 1.33, indicated by the purple line here. To achieve this target, the WMMSC requires 16 dB. The SDR requires 14 dB, while RS only requires 10 dB. The RS outperforms the benchmark by at least 4 dB. So after the optimization, we need to convert this rate optimization to the selection of the proper modulation coding schemes. For the non-RS, it's straightforward because it has only one data stream. To reach the rate of 4/3, we can use QPSK modulation with the rate 2/3 code, which result in an effective rate of 4/3 bits per second per hertz. Yeah, there's some other options. For example, we can use 16 QAM with a rate 1/3 code. For rate splitting, the MCA selection is a bit tricky because the RS rate is comprised of both common and private part. This is an optimization result due to a specific channel realization. We can see that the first group and third group do not contribute anything to the common message. So they are the selfish group. So they only transmit private messages. So on the contrary, the second group contributes 90% to the common message, only 10% to the private message. For group 1 and group 3, we can use QPSK with rate 2/3 code for the private message. That gives the rate of 1.33 bits per second per hertz. But for the second group, for the common message, we can use QPSK with the rate 3/5 code. That gives the effective rate 1.2 bits per second per hertz. For the private part, we can use BPSK with the rate 1/10 code. That gives a rate of 0.1 bits per second per hertz. Now let's look at the BR performance comparison. The non-ICE system does not work at all. There's error flow like this. That means the rate saturation converts to error flow in BR performance. But rate splitting has very promising performance, even in overloaded system. To achieve the target BR of 10 to -4, we need 16 dB. To achieve the target BR of 10 to -3, we need 14 dB. But previously we see that to achieve the target, only 10 dB is required. And there are several reasons for this discrepancy. First reason is that this optimization is derived based on Gaussian input. But in the simulator, we have finite alphabet, like QPSK, BPSK. And the second reason is that this optimization is derived based on infinite block length, while in the simulator, we have finite block length. But this gap also indicates there's a big room for improvement. The system performance can be further improved. So that is our ongoing work. Next, let's look at the multi-carry system. First, I will introduce joint precoder design and sub-carry allocation. The existing works on rate splitting only consider the precoder design. But multi-carry techniques have been widely used in practical systems. So we propose joint precoder design and sub-carry allocation for RS-based multi-carry, multi-group, multicast systems. First, we derive system model. It is not different from our previous work, but this system model is derived on per sub-carrier basis. First, we derive the SNR for the common part, common message for each subcarrier, then calculate the rate. Then we derive the SNR for the private part for the message for each subcarrier, and calculate the rate for the private part. Then we can formulate the optimization problem. Now there are 3 parameters to be optimized. In addition to the precoders and the splitting ratio, we have the subcarrier allocation matrix A to be optimized. And each column of A is the subcarrier allocation vector for each subcarrier. And this problem is non-convex, but it can be tackled by successive convex optimization SCA method. Now let's take a close look at subcarrier allocation. Suppose we have three multicast groups to be served by three subcarriers. So we can have one-to-one mapping like this, or like this. So this is basically OFDMA. Is this the best we can do? No, not at all. Inspired by our work on low density signature, we like to do spreading like this. The message from each group is spread over several subcarriers. And the purpose of doing this is to achieve the frequency diversity gain. The gain can be very large, as we can see from the comparison between LDS and OFDMA. There are two important parameters in LDS. First one is spreading factor. It's the number of subcarriers each symbol is spread over. In this example, spreading factor is 2. A second important parameter is DV. The multiplexing factor is the number of symbols that are allowed to interfere to each other at each subcarrier. In this example, TC equals 2. 2 symbols are allowed to interfere at each subcarrier. From this figure, we can see the spectral efficiency increases as the multiplexing factor increases. The DV determines the diversity gain, and DC determines the multiplexing gain. So the connection between group and subcarrier is called a sparse graph. And this sparse graph can be equivalently converted in matrix form like this. The 1, 1, 0 means this group is connected to the first subcarrier, second subcarrier, but not connected to the third subcarrier. Suppose we have 3 multicast groups, 3 subcarriers, and the spreading multiplexing factor equals 2. Then we have 3 possible group combinations. And G1 and G2, 1 and 3, 2 and 3. The subcarrier allocation is about how to choose the best combination for each subcarrier. And this LDS can be generalized to overloaded system at subcarrier level. Like this. Now, ongoing work is how to use RSMA to further improve the performance. In LDS, when we do spreading, the 2 symbols are same from same constellation. But in RSMA, the first symbol is from the first constellation. The second symbol is from second constellation. And these 2 constellations are rotated versions of each other. If we compare LDS with RSMA, we can see further improvement. That's due to the constellation shaping gain. So we would like to combine the benefits of rate splitting with RSMA. Now let's look at the performance comparison. We use 4 benchmark schemes. The first one is RS without subcarrier allocation. The second one is single stream without subcarrier allocation, which is basically TDMA. Third one is non-RS without subcarrier allocation. The fourth one is non-RS with subcarrier allocation. which is basically LDS. We can see the proposed joint optimization of precoder and subcarrier allocation has best rate performance. And the NARS without subcarrier allocation has a problem, the rate saturation problem. But LDS has very good performance, and performance very close to our proposed joint optimization scheme. But we expect further improvement by cancellation rotation and cancellation shaping. Now let's look at the BR performance evaluation for uncoded and coded system. Okay, let's speed up. We're running out of time. Okay, first we formulate the optimization problem to derive the optimum precoders and the equalizers. Let's look at the performance comparison. We compare R system with non-R system. In such overloaded system, the non-R system has a rate saturation problem, and that rate saturation problem is converted to error floor in BR performance. On the contrary, rate splitting does not have the rate saturation and does not have error floor. Yeah, when the system is more overloaded, the rate performance as well as the BR performance degrades because we have a fixed power. When the number of users increases, the power allocated to each user is reduced. And also each user experiences more interference. Then we extend our study to LDPC coded R system. And we look at two receiver algorithms. The first one is MMSE. The second one is generalized sphere decoding. To enable LDPC soft decoding, we need to derive the log-likelihood ratio for the coded bits. And to derive log-likelihood ratio, we need to have PDF of the common symbol and private symbols. Okay, this is a MF rate performance comparison. We use the same benchmark schemes, and it's basically the same observation as we had earlier. Now let's look at the BR performance comparison. And we use sphere decoding for both RS and non-RS. And we can see the RS system has better BR performance than non-RS system. And the comparison is conducted under the condition that these two systems have the same transmission rate. And here we see the breakdown of performance between the common message and private message. The inner curve shows the BR of the common message, and the outer curve shows the BR of private message. Both perform better than the non-R system. Okay, this brings the conclusions of my presentation. RS relaxes the CSIT requirements and enables system to operate in overloaded conditions without rate saturation and error floor. From our investigation, we see that joint optimization of precoder and subcarrier allocation is crucial to achieve the best performance in our systems. So our error performance analysis validates the practicality and availability of our systems as a promising candidate for future wireless systems. This is a promising research field with many interesting open technical challenges, and we look forward to work with experts in the field. For more information, you can read our published papers. Yeah, that's all for my presentation. Sorry for running over time.
Thank you, Professor Xiao, for the interesting talk. Actually, the time is very very good. Okay, so we already received one question from Neil Baker, and the question is that various simulation results are presented, and what channel model is assumed?
Yes, I think we assume fading channel model. It's a model from 3GPP document. It's a HV is a 3GPP models like EPA. I don't recall exactly.
Yeah, I think maybe he can go to the paper for more detail.
Yeah.
Okay, any questions? Well, actually, I have one question on the OBB application that you discussed at the beginning. It's very interesting. And my question is, when you formulate a problem for OBB MMF problem, you mentioned that based on the QoS requirement of each user and the common rate, let's split it among users does not need to be optimized. So my question is that, why
predetermined.
My question is why the common part can be determined, because the message split actually is also determined by how the power allocated between the common and the private streams.
Okay, let me show the slide. Okay, for example, a common part is this map with temperature and weather condition. Private part can be the presenter, the sign language, text. So the splitting ratio is fixed. We know what is common part, we know what is private parts. So there's no need to optimize the splitting ratio between common message and private message. But what we can optimize is the precoders.
Okay, does it mean that the power allocation between the common and the private part also is fixed?
No, the power allocation can be optimized, but that is already included in the optimization of precoders in our work.
Okay, I see. Thank you, Professor Xiao, for the explanation. Any questions? Okay, if there's no question, well, I think we can end our talk today. Thank you again for the very interesting talk from Professor Xiao. And I would like to remind that 2 weeks later, another Tuesday, I think it's November 23, we will have our 5th RSMA talk provided by Professor Robert Schober. And welcome to join us. Okay, see you next time. Bye-bye. Thank you.
Okay, so thank you, Nina.
Bye-bye, Professor Xiao.
Bye.